Let's look at question 8. The question says that a light aircraft has a weight of 10 kilonewtons. The weight of the pilot and passengers is 5 kilonewtons. So the total of 15 kilonewtons. You are then told that in this particular aircraft, NACA 23012 aerofoil is used, and it has dimensions of chord length 1.8 meters and wingspan 25.6 meters. And you're told there are no flaps. Then you're asked a series of questions regarding what is meant by statements, the takeoff speed at a 5-degree angle of attack at sea level. What does this mean? Okay, and if you look at the answer, which is slightly down the screen, an aircraft will take off when its lift equals the total weight. The aircraft and its payload, okay, now at an angle at attack of 5 degrees, the lift coefficient is 0.6. This data is read from the graph for the NACA 23012 aerofoil. You can see from my projections on the graph, 5-degree angle of attack, roughly 0.6 lift coefficient. Next, you're asked to determine the takeoff speed for this aircraft at an angle of 5 degrees. Okay, so we know that at the point of takeoff, the weight is equal to the lift force. So we can equate the lift force with the weight, make the velocity the subject of the formula, and if we know all the other terms in the equation, which is written on the next line, we can calculate the takeoff speed, which is about 107 kilometers per hour, using the conversion that 1 meter per second is approximately 3.6 kilometers an hour. Let's now look at the topic of stall, which was considered in the previous question, but all the same, let's go through it. The decrease of lift with an increase of an angle of attack is called stall. As you can see from the graphs, and as we mentioned it in the solution to the previous question regarding stall, you notice how critical the angle of attack is. More than 15 degrees, you have a loss of lift. Okay, so coming back to our answer, when the flow separates over nearly the entire half of the aerofoil, the lift reduces dramatically. The separating point is near the leading edge. Okay, and as we mentioned earlier, stall is caused by flow separation and the formation of a wide wake region at the top of the aerofoil. To a certain extent, this is the repeat of question 7, but all the same, in your course, it's very important you understand the meaning of stall, what really happens during stall. Now, you are asked to calculate the stall speed for this aircraft. Okay, so to calculate the stall speed, let's look at our equation. Now, the stall velocity, the minimum takeoff velocity at stall condition, is determined by using the maximum lift coefficient in the equation star. Okay, according to the graph, the maximum lift coefficient is 1.4252 and occurs at an angle of 15 degrees. Let's look at the graph. As you can see, at around 15 degrees, maximum lift is around 1.52. There's an abrupt loss at this point because stall begins to occur soon after this maximum lift. So this would be the critical point. Remember, we are talking about a clean, no-flapped wing, exactly the same here. Okay, although this graph on the right represents the drag versus the lift. Now, let's continue with the solution. Substituting all the terms here, using our value of 1.52 as the maximum lift, we find that the minimum velocity is 67.4 kilometers an hour, or 18.7 meters per second. This ends the solution.